Now we'll start with the first session. Let me introduce the keynote speech, Dr. Kalyan. Kalyan is research scientist and leader NSK Learning for All Alpha Group at MIT. And he holds the PhD in electrical engineering from Syracuse University. Kalyan's research interests are in large-scale machine learning systems. He is currently working on developing a variety of systems that are able to do a variety of machine learning tasks at large scale. I welcome Kalyan to proceed his session.
Good morning, everyone. Thanks for inviting me, Pravin, and thanks for hosting here. My name is Kalyan Veeramachaneni. I'm a research scientist at Computer Science and Artificial Intelligence Laboratory at MIT. Today I'm going to present from JSON lines to latent variable models, and the reason I use that title is 2 years ago was the first time I actually touched some JSON lines. They existed for a long time, but being from electrical engineering, this was the first time I was looking at one. And I'll show you what that means and what happened after we started looking into this, and the journey it took for us from in those 2 years, from going from those log lines all the way to building models that can give us insights or predict certain outcomes that we wanted to. The data that we are using is extremely interesting. It's coming from massive open online courses, and I'll give you a brief introduction about that. This is joint work with some of my students, Colin, Taylor, Elaine, Frank, and the PI, Uname O'Reilly. She leads the group, Alpha Group. I come from a group called AnyScale Learning for All. We started this group about 2 years ago, right around the time we got into this data set. And our goal was to start a variety of data science projects focused on different domains, from medicine, energy, all the way to education. And this was one of the areas that we chose, and it was very interesting and fascinating for us. So around fall 2011, if you have, you must have heard this, or it was a course by Andrew Ng, and it was from Stanford. Around 100,000 people registered. This was a machine learning class. It was an applied machine learning class. And the course offered, this was the first time, although materials for courses were already available online, many universities were actually providing them online. They were blended models as well at several universities. This was probably the first time this was done at a large scale, which included quizzes, graded programming assignments, and this became one of the successful MOOCs from there on. It's still offered in Coursera. Following that, in spring 2012, MIT had its own version of MOOC. It was Circuits and Electronics. Interesting choice. It was not machine learning or AI. It was actually Circuits and Electronics. Around 153,000 people registered for this, and 7,157 people actually graduated. It's been cited a lot and said a lot. What that means is, if we were to teach this course for about 70 years at MIT, that's how many people will pass this course over a period of 70 years, because on an average, the class size for this particular class at MIT is 100. So that was a big deal, because we didn't expect that that many number of people will register and that many number of people will actually finish the course. It's a pretty intensive, hardcore electrical engineering course. It's the first course, the first or second course that you take when you join any electrical engineering department in the country. So as a result of that, 2012, there was a lot of activity, and the year was declared as the year of MOOCs. So the MOOCs stand for Massive Open Online Courses. That's what these courses are. 2014, now we have Coursera, and there's around it claims to have around 7.1 million users and 641 courses from around 108 institutions. This is a quote from Wikipedia. The numbers might be changing and they are evolving all the time. What's also fascinating is the type of courses they offer. For example, here, the course is Inspiring Leadership Through Emotional Intelligence, if I'm reading it right. There are many esoteric courses that I personally would have wished to take if I was in grad school. I tried taking some of the esoteric courses in grad school. They wouldn't pay for it. So I think this is a good option for me to actually go back and take these courses, the ones that interested me. Same with edX. There are also some very interesting courses. For example, Baseball Analytics. I think that is Sabermetrics 101, which is Introduction to Baseball Analytics, how to analyze baseball games. So a lot has been said about MOOCs, and there's many, many attributes, and everybody has a personal take on MOOCs. They include the fact that students can learn at their own self-pace. There are many start and end dates because it's an online course. It's offered several times in the year. For if it's a 16-week course, it's offered three times a year. If it's a 7-week course, it's offered many times in the year. So you can join the course at any point of time, or you can join a new offering when it's offered again. There is a lot of people on the course that interact with each other, help each other. So from different perspectives, it actually touches different in a way, people get fascinated by it in a different ways because of different attributes it brings to the table. Personally, for me, the biggest thing that I like about that is I don't have to wake up at 8 a.m. in the morning for a class. Now I don't go to the classes anymore, but I used to, and when I used to, it was 8 o'clock was terrible. I used to be always late, 5 or 7 minutes late for the class, and I used to be stared at by the professor because I was always late. Anytime, anywhere, access to the material, that's incredibly important. I personally now go over video lectures for some of the materials online, not necessarily MOOCs, but otherwise as well. And it also allows me to repeat the lectures or repeat parts of the lecture many times over. And that's actually a big benefit for me, because if I miss the class, or if I were in the class and actually not present there mentally, I would require to go back and ask someone what happened in the class, or ask someone to explain me what happened in the class. This actually allows me to learn from the video in a repeated manner, even though if I don't understand anything or if I skipped a point. The trial and error in problem solving is a big one. They actually allow you to attempt, the platforms allow you to attempt the problems multiple times, and they give you instantaneous feedback. So that's another big advantage, because in the traditional campus-based learning, you would have to go to the TA's office hours, and there's always a couple of times that you can ask for feedback, considering how, depending upon how large the course is and how many people are in line there. This actually gives the feedback, although I'll show that the feedback is right now very superficial in terms of it just gives you whether right or wrong for one particular course that I'm going to give you examples for. But they're working on a lot of more additional ways of giving feedback, much more fine-grained feedback when students are trying to solve problems. And last but not the least, it's a wonderful opportunity for me to learn inspiring leadership through emotional intelligence. That's, I don't know what that course means. I just meant to say that there is a lot of esoteric courses that we can try to look into and learn. So what I'm going to talk about is I'm going to talk about the structure of the MOOCs, the data that's being recorded and collected in the MOOCs, data set we use, and the properties of its size, and how we organized it, and how we scaled up our data science on that particular, on this particular data set. I'm then going to talk about challenges of feature engineering, what does it entail, how we are trying to scale up, and I'll explain what feature engineering means in this context and what complexities and challenges it brings with it. We'll focus on one particular problem that we just finished and wrapped up and developed an algorithm and built several models, in fact. It's called stop-out prediction problem, and I'll explain what that problem is. I'll show you the different methods we use and some results, and finally we'll conclude. So the course that I'm going to use the data from in this particular presentation is the first course offered at MIT. It's as I told, it's the 6.002X Circuits and Electronics. It's a Circuits and Electronics course. It had roughly 14 weeks. I think the 14th week was the final. There was a midterm in 8th week, and there was weekly modules. So every week it was a different module, a different topic. And there was some structure to the course. There were assignments every week, and there were labs every week for the students to try and get graded. So the structure of the course, as I said, it's split into multiple weeks. And within each week, there are actually lecture sequences, which are actually 15-minute videos. You can change the speed as you browse, as you go through the video. You have audio accompanying the video so that you can read the audio as well. The 15 minutes there is some notion of that an ideal attention span is only 15 minutes. So there's the lecture itself is broken into 15-minute subsequences. And there's, in between two videos, there are some in-lecture quizzes which just test the student or ask questions on what was just being presented on the video. So what's interesting is, as I present this, every click the student makes on this video, every time he or she changes the speed, plays, pause the video, all of this is collected in the back end for us to analyze. Even the answers that they give to the lecture quizzes are also being recorded. So there's millions of events, millions of clickstream events that are being recorded as a result. There is a book. It's an ebook. Every page is uniquely identified by a different URL, so we actually know when a student goes to a URL, goes to a book page, we know exactly which book page the student went to, and we record it in the back. There's roughly I think there's thousands of pages in this book, so there's a lot of URLs that correspond to different pages in this book. This is the problem solution try. Here, a student has tried the first subpart of the problem. The autograder tells that he or she is right, then they try the second problem, and they try to check, and then the autograder tells you're wrong, and they can attempt it multiple times. Every time they attempt again, it's recorded in the back end in our databases. Finally, another most interesting source of data from this platform is when students interact with each other. So thousands of students go to this discussion forum that's actually on the platform itself, and they talk to each other, they ask questions, they answer each other without even, sometimes if the TAs or the instructors are not there to intervene or answer, the students answer each other. And at the end of the course, you do get a certificate. There's a certificate of completion that you can get. This is an example just we pulled out from somebody's website that had displayed this. So what do we do with that sort of data, and what's our agenda? We try to go from all the way from integrate to visualize. What we mean by that is when the data comes, it's in different formats. We try to integrate that into a standardized format. We create a shared data model called MoveDB. That's sort of a shared data model in which MIT, Stanford, as well as other universities are going to put the data in. We built that shared data model capturing every little nuance in the data. Once we do that shared data model, we are now able to write software that could be reused across the board, and we already started exchanging software between universities so that we don't have to share the data, but we share the software that works on the shared data model. And then we try to process and model, which is what we call MOOC intelligence. I'll show you that's actually the topic of this talk, so we'll go into detail about that. And then we visualize the data as well. So here's how a JSON line looks like. It's just an event trace of what happened, what did the user do, what's the IP address that the user came from, what's the URL that the user visited, and what's the timestamp. We transformed that data into a sequence of tables. This is here the trace of students' navigational events. One interesting thing is JSON lines are actually a bloated storage format because they repeat the URLs, which are sometimes long. We encode the URLs into IDs, and we create a URL dictionary that significantly reduces the size of the data almost by a factor of 10 in this particular case. The data regarding students' submissions are stored in a separate table where we identify the problems by ID. We store the hierarchy of the problems because there's problems and there's subparts of the problems. Every submission that the student does, the timestamp, the attempt number, the particular answer, the exact answer that's given by the student, everything is recorded in this database. In the back end, we also record the type of the problem, the assessment information, the grade activity. Sometimes these assessments are done by their peers, so we also record peer assessments. So sometimes their submission is assessed by multiple assessors, so that's also recorded. So we have a lot of data in the back end to actually analyze how students are doing problem solving and how they're being assessed and how they're proceeding in the course. So as I said, the first course has 154,000 registered students. There were roughly 17.8 million submission events. What I mean by that is there were roughly 17.8 million attempts in aggregate from all the students that attempted any problem in that course. There were roughly 600 problems in this course, so there was a lot of multiple attempts, a lot of students trying multiple attempts. One student actually had a very skewed distribution and almost had 200 attempts for some of the problems. There were 132.3 million navigational events. These are curated events because we reduced the size of the events by removing repeated events. But overall, the course had around 200 million or more than 200 million events. Around 90,000 forum posts. But is this big data? Actually, when we reduced the size of the data, it was roughly 70 gigabytes for one course. So from one perspective, yes, if there are 180 of these courses being offered during the year, it will create it will create more than terabyte worth of data. But is that really big data? Because if we actually transform them into this shared data model where we reduce the size, we encode everything, then it's actually not that big. It's actually 7 gigabytes. That's one of the questions that we ask constantly. Is this really big? So one of the things, as I mentioned, we created the shared data model, which is now sort of a comprehensive model that captures every nuance of this data, and we write software on top of it. As a result, we launched the project called MOOCDB project. The data model itself is called MOOCDB. Now what we are doing is we are trying to build a number of platforms that sit on the MOOCDB project. So there's a website on CSAIL's website. It's called mookdb.csail.mit.edu. If you're interested, you can look into the different platforms that we are building. So what sort of research questions everybody has been asking? There's a lot of questions about who registered in these courses, who finished the courses, what sort of grades they got, the demographics information, the statistical correlations between the educational background, whether the particular student was a bachelor, master's, or a PhD, and their grades or their completion. There's a lot of questions about trajectory, what navigational paths the students are taking through the course. It's often the case that what we believe the way students should proceed with the material is not the way they actually proceed, a large population of them. So we are trying to mine that information to understand if there's actually multiple pathways to the same material. There's very general questions about learning and education, the learning styles. If there's a lot of students who are interested in videos versus books or forums. There's actually very different categories of students. Some like interactions, so they go to forums a lot more than they actually go to videos. I think they go least to the book in the whole navigational events when we explored how many events were by one category of the course. So here are some simple examples that the visualization platform enables. Here's the 6W2X course, and this is basically the percentage of students that got the certificate among the students who actually registered for a particular country. So for this course, Circuit and Electronics, a lot of concentration was in Eastern Europe as well as Eastern Europe and Spain and I think and then UK. There was a lot of certificate winners. This is another course where this is the course from MIT. This is another course where a lot of people succeeded in completing this course were from Russia. So any guesses what that course is?
Computer science.
Cryptography. This is another standard sort of a plot that we generate from a course, and this is an event timeline. It just counts the number of navigational events on a weekly basis, on a daily basis. This is a very classic plot. It's been shown again and again for several courses. And this is in aggregate for all the students. If we split this by country, because we do know the IP address from which the student logged in from majority of the times, if we split this data by countries and then plot this again, it looks the same. Any guess why those spikes are? Pardon me? They're the deadlines. They're right before the deadlines. And as you see, that actually one of the biggest problems that we are trying to address is the fact that out of all the people, that many large number of people who register, a lot of people actually drop out. We don't call it dropout, we call it stop out, because these students are not your typical college degree enrolled students in a college degree program, so we call that stop out. That just means that they stop engaging with that course. This plot goes down as time goes along because we have far less students as the course goes along. The initial peak is a huge number of students who registered, and slowly the students stop engaging with the course. So then the classic question, where is the big data? It's not the size, because it's only 7 gigabytes. We deal with 1 terabyte worth of time series from ICUs and medical time series all the time. So it's actually not the size. So I'm going to shift a little bit and talk about why there is big challenges with this data, even though if it's not the size. So one of the big challenges with this data is if we want to learn something, a predictive model, and do machine learning on this data set, one of the biggest challenges is to do feature engineering. So what I mean by that is if you wanted to predict who's most likely to drop out or stop out from this course based on the data so far, we would have to posit a number of variables. For example, maybe the number of tries the student has, attempts the student does on the problem, right? Or maybe the time spent on the course is an indicative of future stop out. What it means is if we actually see if the student is spending less and less in time, then we will predict that actually he's going to leave the course. You would see that it's actually that's not a great indicator. We tried that. That's not actually a great indicator for us in our prediction. So the biggest challenge in this data set is to actually come up with these features, come up with what we call as features, is the variables, and then extracting those variables or operationalizing those variables from our data set. That takes a life of its own. And I'm going to show you a few examples of how complex these features can get and what sort of attributes these features themselves have. And we extract features on a weekly basis. We extract variables from every week's worth of data for every student. And the reason being every week in this particular instance in this particular course is a separate module. So it makes sense to actually separate the data on a weekly basis and extract the engagement variables on a weekly basis. So the classic procedure in machine learning, once you have your data completely organized, and once you have defined a problem that you would like to build a model for, in this case, predicting a future stop out. The classic case is a couple of us sit around and we think and we say, okay, maybe this will predict the stop out, maybe this will predict the stop out. So we pause it and then we figure out how to actually go to the data and extract it. And then we literally write the code and operationalize that and write the software to extract those variables. This whole cycle is extremely iterative and it takes a long time. Once we have those features per variables, we can actually do supervised or unsupervised learning, which is we can cluster or we can actually predict stop out as is the case in this problem. So what are the types of variables and why am I talking a lot about those variables and why is it challenging? The variables we classify can be simple, complex, and derived. What I mean by simple variables is they do some sort of count or create aggregate for a student for a week. So for example, time spent on the course during the week, number of problem attempts made during the week by that particular student. These are simple aggregates. You can go to one of the tables in our database and you can just simply add them up and you get a number out. So these are very simple set of variables that we can extract. The complex variables usually require us to extract data at the intersection of two different tables. What I mean by that is there is a table that stores just the navigational transactions or navigational events for the student, and there's a table that actually stores the submissions. So for example, a variable like number of times the student goes to the forums while attempting problems requires us to go into two separate tables and extract timestamps of every two attempts, subsequent attempts that the student had during the week, and go to another table and watch whether he actually went to the discussion forums and participated in that. So that's what I mean by complex features. They usually require intersection of two or more modes of students' operation, and what that implies is two or more data sources. As a result, it requires a more complex scripting and processing, and it requires, because of the number of millions of events in this case, it also requires a lot of time in terms of the processing power. The other biggest challenge in defining complex variables is actually curation and sometimes even manual processing. For example, if we want to extract a variable, on an average, how close to the deadline does this student start submitting problems? Now, the deadline information is not stored in the database right away because it's one of the things that in the course structure, so we don't get access to that very easily. The second thing is the deadlines are actually fudged around a little bit, so they change it to adjust for a large cohort of population, ranging from one, it's 12 a.m. till the last 12 p.m. is done, or 12 a.m. is done in any part of the earth. So getting the deadline information for every student and getting the deadline information from the course for different components is actually very challenging. Ultimately requires somebody to manually do it. It's not that complicated to do it manually, but it requires us to manually curate that and get that information. The third type of variables are derived variables. What we mean by that is they combine two or more features to form a new feature. They are derived based on a mathematical function. Usually, sometimes domain experts, the one that know about the course, can actually posit some variables or posit some combination of the variables we already extracted, depending upon the structure of the course, because they know very well the structure of the course. Examples here include the ratio of correct submissions to the total time spent in the course during the week, trends, percentiles. So essentially comparing, not actually extracting variable for that particular student, but also saying that how does this value for the student, what relative standing does he stand in the class? Now all of these are essentially human intuition based. We can't automate this process. We would have to ask people. We would have to get input from people. And I'll show, we did that experiment as well to actually get variables from a lot of people, and we launched a platform where we can now have the crowd propose the variables and extract the variables. So the real value in this big data can only be derived, in this data, can only be derived by actually coming up with these complex features and complex variable. Essentially, that's the biggest challenge in this data set, is coming up with these complex features and complex variables and derived variables that explain the behavior of the student on a weekly basis. So we went ahead and did this. We proposed ourselves. We asked a class that was called 6.mitx class, and it was about building the platform, the online learning platform that I just showed. We asked the students to propose some variables, and I'll show you a few examples of the variables they proposed. We ultimately went out to the crowd. We created an online platform for the crowd to actually propose the variables, comment on each other's variables, and even subsequently extract those variables and submit scripts for us to actually extract those variables. So what sort of input did we get when we asked 6.mitx? This is just in code from one of the students. There was like 30 people who participated in this. We got around 30 to 40 ideas from this exercise. They were extremely detailed, as you can see. You can look at the aggregate duration each student spent on the resources. You can average the total time spent over all students, and then further away from the average, they are more likely they are to drop out. This is actually only possible for from a human intuition. So only humans can input in that detail why a variable, what sort of variable one should extract, and what sort of the reason behind it. There was a lot of intuitive variables that, as I'm showing here as an example. So how does one participate? You can participate too. There's a website we have. It's called featurefactory.csil.mit.edu. We we encourage to go there, take a propose. You don't have to extract, comment on existing variables. And if you're interested, actually look at the variable, look at our data model, and extract those variables. Write scripts to extract those variables. What is very interesting about this, when we self-proposed versus when we asked the crowd, when we self-proposed, we knew that we were the ones who were going to write the extraction scripts. And it turns out that we are very conservative and in our creativity when we know that in the end we have to do the work. But the crowd was very, very open-minded because they knew at the end of the day, it just goes into an idea bank from where we will extract those feature scripts. So it's very, it was a very interesting exercise to see that why we didn't actually posit the variables that the crowd did posit. So here are some variables that we actually came about. I would actually skip. There was a lot of derived and complex variables. The red ones are some of the ones that actually crowd came up with, and I'll show how important those variables ended up in being for stopout prediction. So predicting stopout, essentially, as I've been mentioning, is to actually predict a future stopout for a student, whether or not he or she will stop engaging with the course from the current behavioral data. This is important because we can actually do interventions. There's already the interventions being designed to actually encourage the students to continue the engagement. This is sometimes important for logistics. We define the stopout as when the student actively stops attempting for problems, not actively engaging or not coming to the website, but actually attempting the problem. That's what we consider as engagement. We also try to predict a few weeks ahead, and we change that. How many weeks ahead we try to predict, we change that, and we build multiple models for different, each time we change the lead. For example, here we are thinking of using 2 weeks worth of data, and we want to predict 4 weeks ahead. We can change that 4 weeks to actually, we can actually change that 4 weeks to 5 weeks or 6 weeks, and each time we change that lead, the prediction problem itself changes. So our cohort also was actually some fundamental properties. We actually, even though there was 153,000 students, there was many students who did not even attempt the first homework or first problem. So they were not engaged from our definition of engagement to begin with. So we first split those out because we can't build a model for them. Then within the attempts, within the ones that actually engaged in the course by attempting the problems, there were multiple cohorts. There were cohorts that actually never went to the forums or never did discussions. They just went to the course, attempted the problems, and that was the largest proportion of students, around 44,000. We had a significant proportion of students that actually went to the forum and also engaged with the course. There was wiki also in this course, so a lot of students edited the wiki content. Wiki is supposed to be informational material about the course, not about the course structure, but actually the technical parts of the course. So there was 4 different cohorts that we separated this, and by far the most interesting one are the no collaborations and the forum only cohort. The forum only cohort is the cohort that goes to the forums as well. So the types of models we build is we build logistic regression models or hidden Markov models, and I'll go into a little bit of detail, and then you can start combining logistic regression and hidden Markov models. And there's many combinations here. There's discriminative models. We have a platform that builds thousands of classifiers in the cloud. So we tried that as well, and I'll show you the results we are getting from that. The whole point of this exercise was to emphasize that and you'll see the emphasis as we go through the results for some of these models. So the first one was logistic regression model, where we tried to change, given what we mean by lag is the amount of data or the week we are in right now. So for example, the first block here, what it means is we have the first week's worth of data. The course is proceeding. We have 1 week's worth of data. We are trying to make a prediction for the second week, third week, and so on, and all up to the 14th week in the week. That is the x-axis. So what it means is that we haven't, we don't have any information after the first week. We're just using first week's worth of data, and we are trying to predict ahead. As we go along, we have more weeks worth of data, and we are trying to predict ahead, predict 1 or 2 weeks, depending upon how many weeks are left in the course. I don't know if everyone is able to see the numbers, but it turns out that even with first week's worth of data, and higher this number, the better the accuracy is. This is the area under the curve metric for a receiver operating curve. So essentially, the higher the number means it's a better accuracy. 0.7 is a reasonably good area under the curve. 0.9 is excellent. For every time we have, if we are trying to predict the next week, we are able to do really well. We are able to get 0.85, 0.86 area under the curve. But what is very interesting is if we actually take 1 week's worth of data and try to predict 14 weeks ahead, which is almost the end of the course, we are still able to predict with a reasonable accuracy of 0.7. And the reason, and that's incredibly interesting because a lot of questions have been asked in this in massive open online courses that why are students stopping out? And is it something that we did? Is it something there's a problem with the material, or there's a problem with the instructor, or there's any problem on the platform? If we are able to predict for the students whether they're going to stay in the course or not, just based on 1 week's worth of information, essentially those cohort are not of interest to us because they haven't been exposed to any material yet. And yet they had behavioral signs and attributes in their navigations that indicated to us that they were going to leave the course anyways. So there's this sort of post-prediction analysis is what we are engaging in right now, taking all these predictive models that we built. By the way, these are 91 models because there's 91 different prediction problems here, so there's actually 91 models here. Then what we do is we try to identify, okay, we talked about all these complex and derived variables. What mattered? What did matter in actually predicting this? So we do something called randomized well-distributed regression where we resample the data multiple times, and each time we build a model trying to use as minimum number of features as possible and still achieve the same accuracy. What that allows us is to regularize, and we get a subset of features giving us the same accuracy, and we do that 1,000 times over, and we average out and we see what features actually matter. So here's just a summary of what features actually matter. Higher the weight here, the more it mattered in terms of prediction accuracy across the board on those 91 experiments, 91 models we tried. So the complex natures, all those ones that are annotated as 200 and above, were actually proposed by the crowd. So the complex features and the derived features actually mattered. The duration did not matter. The amount of time you spent on the course did not matter as much. There was no trend in it. There was no actually, because students suddenly stopped out in the course. Rather what mattered is the pre-deadline submission time. The time before the deadline, the student tries to submit an answer. Right. So, and this is just an example of the type of variables that mattered, and from the week which they mattered here. The problem is that we take 2 weeks worth of data, so we are at the 2-week point in the course, and we are trying to predict the last week. And these are the variables that actually mattered. So the total time spent in lectures does matter, but not total time spent in the entire course. So they could have gone to forums and talked a lot, but that didn't matter. A pre-deadline submission, attempts percentile, which tells how, relative to the entire population, how many attempts does this student have, that mattered as well. So a lot of analysis we are doing right now is post hoc, taking these models and analyzing what mattered and what didn't matter. And a lot of evidence suggests to us that actually a lot of input from people that we got in terms of defining our variables did matter, and nothing else actually mattered, the ones we were extracting ourselves. Then we try to build hidden Markov models. And in the hidden Markov models, what is assumed is that there's actually a latent variable, a latent state, that is generating this data. So there is some state of engagement. The student is interested, or there's multiple levels of interest that the student has that reflects in the way he navigates or the way he interacts with the course, and that's actually exhibited in our variables. One of the biggest things about hidden Markov models is we don't know what sort of how many support or how many states are there for the latent variable. So we change the latent variable and we try to predict models. What we start to get is we start to get a higher accuracies than we were getting in some cases